Good morning. Welcome to Krishna's classroom. Let us continue with our uh, discussion of both Riemann integral, integrability, and Lebesgue integrable together. It's a comparative study, but you know that we have introduced Lebesgue integral because of certain shortcomings in Riemann integration, and or rather certain limitations of Riemann integral. And for deeper structural reasons also. And our effort had been extremely successful. Naturally, we had been checking at various stages whether we are on the right track by comparing the Riemann and Lebesgue integration or various features of the Riemann and Lebesgue integration. Now let us try to characterize Riemann integrability in terms of the word measure. Now this is the point, because when we were working on Riemann integral, we never used this term. But then, of course, in a disguised form, we had been working on this. Well, let us briefly recall certain facts. Recall the following. Recall. So something that we want to recall is f is Lebesgue integrable over E if and only if f is measured. Provided measure of E is finite and f is bounded. Now this theorem we have proved under these conditions. So if E is a measurable set with measure of E is finite and f is a bounded function, then we have the result that f is Lebesgue integrable over E if and only if f is measurable. Now just look at how we define Riemann integral or what functions we define Riemann. So in the case of Riemann integration, we had the following assumptions defined on compact intervals that is of the type so that was our E. Okay. Then we looked at only bounded functions. functions AB. Then we found that F is Riemann integrable on AB implies F is Lebesgue integral. And the Riemann integral of F, this is equal to the Lebesgue integral of F. That means the integrals coincide. Now this is we have assumed F is bounded, AB is a compact interval. In that case, F is Riemann integrable. I mean, that does not assure that F is Riemann integrable. But if F is Riemann integrable, then integrable, then it is also Lebesgue integrable and or integrable in the sense of Lebesgue, and the two integrals coincide. Now this is something that we have, and consequently from what we proved, in the previous theorem, the 7 F is okay. So this is what we get, right? F is Riemann integrable on AB, then F is implies F is Lebesgue integrable, and since it is Lebesgue integrable, it is also measurable function. And with all these conditions, that means we are working on an interval of the type AB, that is a closed bounded interval AB, and F is a bounded function in that case. Now we are in a position to state something deeper than this. After I give the statement, I will make some remarks. So this is the theorem that we are going to, the characterization that we are going to characterization of Riemann integrable. Let F be a bounded function on a compact interval Now there are two things here. See, Riemann integrals were defined only on intervals, that too compact intervals. and it was defined only for functions which are bounded. Okay, so that is one of the major limitations of the Riemann integration theory. Whereas when we generalized it, we could get away from that. And if you just look at the statement here, you see, we had said that if E is it could be defined on what are called measurable sets in terms of Lebesgue measure. Okay, and we were talking about, see, look at this result, F is Lebesgue integrable over E whenever measure of E is finite and F is bounded, then F is a measurable function. This sort of generalization was possible. Okay, so let me complete the statement of the theorem. Okay, so we have this, that F is assumed to be a bounded function on a compact interval AB. That's the assumption, where of course the Riemann integral is defined. Okay. Now, what else? Then we are going to say, of course, AB is contained in R, part of it. It's a compact. Needless to mention that. Okay. Now let me then F is Riemann integral over a compact interval AB. If and only if the set of points AB at which F fails to be continuous, or what in short we are talking about the points of discontinuity of F is in the sense of Lebesgue measure. Okay. Now this is a Lebesgue measurable set, and the Lebesgue measure is given by B minus A. That, and what assures the Riemann integrability is the fact that the set of points where F is discontinuous is a set of measure 0. This is a necessary and sufficient condition. Okay. So F is Riemann integrable over AB if and only if the set of points of AB at which f fails to be continuous which is the set of, is called the set of points of discontinuity of f is a set of measure 0. Okay, right. Now, before I go to the proof of this is a characterization because it's a necessary and sufficient condition. Okay, this is the significance of this. Having done Lebesgue integration is only to check how the two things compare, or is the Lebesgue integration theory a genuine march forward from what we could do for what we could have. So that is the only purpose of this theorem. It happens that mathematics progresses in steps, and if you are generalizing something, you would like to check that the new concept that you have introduced is essentially the same as the concept from where we started off for those class of functions or those class of objects. Now, that's the general practice, and we are doing exactly that, and that's why, see, you have the Riemann integral and the Lebesgue integral coincide. So it is not, it's all the same. But you know that in a general scenario of just taking a measurable subset E of finite measure, and f, even if we keep f bounded, okay, it may be Lebesgue integrable, but may not be Riemann integrable. For instance, you know that the Dirichlet function that you have has this property. It's a Lebesgue integrable function on the interval 0, 1. We are taking the characteristic function of the rationals or irrationals, it doesn't matter, whichever it is. Now, it's a bounded function on that interval, and the interval 0, 1 is a measurable set. Now, this function is not Riemann integral, whereas it is Lebesgue integral, and it is in this context, in the context of this theorem, it would be nice to see what happens to those functions. Okay, just leave it at that, and let me also recall the form. Okay, if you recall our discussion on Riemann integration, you would call, at some stage we introduced the concept of what is called oscillation of the function at a point. The oscillation is essentially the following. Says the oscillation gives you the measure of discontinuity at a point, or what you call the jump. It's a jump discontinuity. We are working on functions which are bounded, and what we have is just discontinuities of the first kind. It's a jump discontinuity. And the measure of that is given by what is called the oscillation, which was denoted by the following: omega at x, or I don't know whether it is omega xf or omega fx. Whatever be the notation. This is the oscillation. And obviously, at points of continuity, this is 0. The oscillation is 0. At continuity, at points of continuity, the oscillation of F zero. At points of discontinuity, oscillation is not equal to 0. So oscillation actually measures the discontinuity at a point. Now you look at the set of all x at which oscillation is not equal. Okay. So we looked at the oscillation of, now we consider okay. So the set of points F has non-negative or non-zero oscillation. And this is actually non-negative oscillation because the way in which we have defined it. Now this, we said we proved that F is Riemann integrable on AB if and only if the points of discontinuity this is called the with non-zero oscillation. Is what you call a null set. To recall how the null set, how some set was adjudged as null set, is the following. You pack the set of points in in intervals, open intervals, okay, and then for each packing you have then a length. Okay. Now try to pack it as efficiently as possible, in the sense that we try to pack it in these sets of discontinuity in intervals, and then look at the corresponding to each packing, write down the length of the packing. You look at the infimum of this over all such packings. Okay. If that is 0, then you call the set a null set. I mean, this is roughly what you mean by null set. Okay. Now we use the terminology null set at that time. We didn't use the terminology that this particular set has measure 0 at that time, because the concept of measure was not introduced. But essentially, you observe that the concept of null set is, in this context, the situation where the measure of the set being 0. Okay, so that's one remark I have to make. Now now we can try to prove this theorem. Okay, so this is just a remark. Okay, let us now prove this theorem. So we first start with the assumption yes. That is the class of all Riemann integrable functions on A. Now you recall how we got the Riemann integral. The function is Riemann integrable. See, you had a partition of the domain, okay, and then corresponding to each partition you had what is called the upper and lower integrals, and then we said f is Riemann integrable. The upper integral is equal to lower integral, not for each partition, but the upper and lower integral. You had for each partition you had a upper sum and a lower sum. Okay, and then you have all sorts of inequalities which essentially led to Riemann integral. So you had the situation that upper integral is equal to the lower integral, or vice versa. Okay, so the upper integral AB is equal to the lower integral. That is the condition that we. This is the upper integral, this is the lower integral. lower integral. So the equality of the upper and lower integrals was the criteria for Riemann integral. And in that case, we said the upper integral or lower integral is called the Riemann integral. Once again, in this context, you can look at functions. You look at all continuous functions with a finite set of discontinuities on bounded functions on the interval AB. They are integrable, when Riemann integrable, where the upper and lower integrals coincide. Whereas if you look at the Dirichlet function, namely a characteristic function of the set of rationals on the interval 0, 1, you see that here the upper integral and lower integral differ, therefore that function is not Riemann integral. Okay. That means, how do you arrive at this upper integral and lower integral? So, what it says is that there are sequences of partitions of the interval AB say En and En prime for which you have limit n tending to infinity of the upper sum corresponding to this, that is this is another characterization in terms of the upper sum and the lower sum. Corresponding to each partition is actually taking the interval AB and breaking it up. A equal to x naught, x1, b equal to xn, xi minus 1, xn. This is the partition. And corresponding to each of this partition, you can define what is called an upper sum and a lower sum by bringing in, approximating by what are called rectangular areas with the height taken as the supremum of f on the corresponding interval, and the lower sum with the height of the rectangles as the infimum of f on these intervals. So, corresponding to each partition or different partitions, you can have an upper sum and a lower sum, and this property is equal to 0 whenever f is Riemann integral. So, that's a characterization of the Riemann integration, the definition in terms of the partitions. Now, UPF, UFPN and LFPN are the upper and lower sums with reference to the particular partition Pn and Pn prime respectively. With respect to the partitions respectively. So this is called the upper sum and this is called the lower sum. Now, one thing that you have is that if you take any partition and refine it, then the lower sums increases, okay, and the upper sums decreases, okay, right? Refinements of the partitions increase the lower sum and decreases the upper sum. We are just recalling the facts from Riemann integration. Therefore, you take Pn and Pn prime and then you go for a refinement of that. Okay. So, each stage when you refine it, you get this. Okay, right. So, we are assuming f is Riemann integrable. Therefore, the limit, the upper sums and the lower sums tend to the same limit. Okay, therefore, so we replace a refinement of Pn prime and we shall again designate the refinements by Pn. So what we have is this. We then have Pn plus 1 is contained in. Recall Pn is a set of points on 0, 1. So what it says is that all the points that are in Pn are also points in Pn plus 1. That is what you mean by a refinement. Okay. That is Pn plus 1 is a refinement of Pn, and we shall use Pn plus 1 is a refinement of Pn, and we take Pn equal to Pn, which means that both here and here we work with the same partition and not different partitions. But in general, this result is true for different partitions. But if f is Riemann integrable, then of course it doesn't matter at all. So now we bring it to the language that we are using in the context of Lebesgue integration. Let us see. Now you recall, this is what you have. You are approximating the given function from below by a step function, from above another step function. Okay. So these step functions are subordinate to the partition Pn. Okay. So let us introduce some notation. Let for each index n define phi n be the lower step function and psi n be the upper step function approximating f. See, it's something like this. See, take 0, 1, take partition like this. Suppose the function is like this, then what we are doing is have a lower approximation. Lower approximation would be okay. The lower approximation is in this case this one and this one. This is the lower approximation. So the function f is approximated by these step functions. What we are doing is we are taking the infimum of f on these subintervals. That is the lower approximation. Then the upper approximation is by the following. Okay. So you replace this by this one on this interval, and on this interval it is going to be this one, and on this interval it's going to be these are the. So this gives the upper approximation. This gives the lower approximation. So you call this psi n, and this is in this case 3 for n equal to 3. Okay, so that's the partition. Okay, so this gives psi n and phi n. Now LFPN this is equal to, that is the lower integral, a to b phi n, and UFPN to integral a to b. So step function. Now one is computing this area. This is the lower integral, and the upper integral is computing this area. So the actual area is, if at all it is something that you can reckon, then it is going to squeeze between the upper integral and the lower integral. This is true for every. Then see, is phi n and are integrable. Are integrable functions such that which we shall designate by now. You see, you have this phi n is a monotonically increasing function, and psi n is a monotonically decreasing function. Also, you have integral a to b psi n minus, that is the area enclosed here in this in between. This is equal to, okay, we are working on the limit of this. This is equal to limit n tending to infinity of is equal to 0. Therefore, what do we have? So we have now translated everything into the language that we are familiar with now, and we have made it in such a way that we can apply the previous theorem. Okay. From the six that we have proved, we infer that the sequence phi n converges to f, and f pointwise see, we are using the language of Lebesgue integration now. That means except on a set of measure 0, these functions are assumed to, when they are measurable functions, they converge to f almost everywhere pointwise. This is what you. Or the set of points where these sequences fail to converge pointwise is a set of measure 0. So we have used the language of integration. Okay, I think I have, this is not a question. So let me denote by fail to converge to then by the Riemann integrability we have measure of now what we do is let E naught be equal to E union the points of partition. What about the points of partition is countable. Okay, the set of points of partition is a countable set. And hence of measure 0. and therefore of measure so what we have, so this is what we have defined as E naught, which implies is equal to 0 because E is contained in E. Now what we claim is this. On the complement of it, this is what it is. So that the set of discontinuity of f is a set of measure 0. So if f is Riemann integrable, then the set of discontinuity of f is a set of measure 0. Okay. So let us do. This is what we want to. So we prove that at all points on AB slash E naught, the function is continuous. Okay. So let x naught belong to so let epsilon positive be given. Since it's not and these are the set of it's not. We may choose a natural number n naught such that minus epsilon is less than or equal to f of x naught is less than or equal to psi x naught and less than plus this inequality is valid, because what you have is this, that phi n naught x naught or phi n x naught converges to fx. It's an increasing sequence. Psi n x naught is a decreasing sequence which converges to fx naught. So once you fix epsilon, see, this one is going to lie between these two. Okay, so this, or you would have had the value phi x naught is there. So see, this is suppose, then this is then what you say is this, that is, this is, and this is, so this points move in this direction, this points move in this direction. That is all connected with the particular point x naught. So n naught really depends on epsilon. So x naught we are choosing, it's not a partition. Okay. So x naught is not a partition point. And therefore, what we can do is this. Of Pn naught, a particular partition Pn. So we may choose delta positive such that the open interval is the open interval I n naught by Pn naught containing what I mean to say is this. You know that you take the partition Pn naught. Now there is an open interval, say let us call it In naught, which contains the point x naught. Then you can find a delta such that x naught minus delta, x naught plus delta is the open interval is contained in In. This is what we mean. Such that this is what you have. So you have to work with the Riemann integration theory by your side. Then only all these things will be clear. But it will be worth doing, such that if mod x minus x naught is less than delta, then psi n naught so you see that phi n naught x naught and psi n naught x naught is related to the what is called the infimum and supremum of f on this particular interval I n naught. That is from where you get this. Okay, and that implies if mod x minus x naught is less than delta, then you have two inequalities. One this and the other one mod fx minus f of x naught is less than. Okay. You have these two inequalities and use these two inequalities to come to this conclusion. Okay, right? And thus we have proved that except on a, if f is Riemann integrable, then except on a set of measure 0, okay, the function f is continuous, okay, or the set of discontinuities of f forms a set of measure 0. So that proves one part of the theorem. Okay. Now what we do, the next part is essentially prove the converse. Prove the converse. What is the converse? The converse says that if f is continuous at almost all points in A, that means the set of discontinuities of f forms a set of measure 0, then you will have f Riemann integrable. Okay, so that is the part of the theorem that we are going to. So essentially, what we were calling a null set is essentially a set of measure 0. That means the set of discontinuities can be packed inside a set of measure 0. So this is the idea. So I think since the proof would take slightly longer time, I would probably do it in my next lecture. Okay. So thank you very much. So the converse will be proved in my next lecture. Okay. Right. So I will just put it here. The converse what is the converse? The converse is that if f is continuous on a set of, except on almost everywhere, then f is Riemann integrable. and which is essentially the Lebesgue integral. And of course, this theorem tells you much more than simply f being measurable, because you recall the previous theorem, what I said is that, see, if you take these functions where Riemann integration is applicable on the interval AB, then what we can prove is that f is a measurable function. Okay, and then we also have proved that if E is a set of finite measure and f is bounded, then see, measurability would ensure what is called the Lebesgue integral. Okay, right. So we have that theorem, and it's a special situation. We are linking up Riemann integrability and Lebesgue integral. So what remains to be proved is that if f is continuous almost everywhere, then f is Riemann integral. Or we get a much better insight into the nature of the function which are Riemann integral than just saying it is measurable. Okay. Thank you very much. So we'll continue with the proof next time.